Continuing this as taught, sort of, demonstrated in some cases, which is very good. But anyway, so we're on light, which is really, and scatter, which is really going to be important, I think.
We have to scatter it of very fine particles, much smaller than 1/10 of a micron. Dust particles would work very well. Now, the theory of light scattering is extremely complicated, but I will be able to convince you that if I scatter the light over an angle of 90 degrees, so it comes in like this, and it scatters over an angle of 90 degrees, that it becomes 100% linearly polarized.
Now, I don't think that's terribly complicated, as he's already established that the higher, this Brewster angle creates 100% polarized. This would be over the Brewster angle, so it's less than 100%. But, well, who knows?
I will stay on the center board. Suppose I have light coming in like so. And I have one light photon. I concentrate on one to start with, and it happens to be that that light photon is linearly polarized in this direction. And so the effect...
So again, I would argue there's no E vector, there's none of that stuff. This linear polarization just means the light is in parallel. That is, it's not diverging. It's in the bits of the photon are parallel because they were emitted from the same electron, presumably. And they're just a little bit out of alignment. And the electron moved between the points where it emitted the light some distance. But the light is going to be shot at exactly the same angle from a different location. So they are parallel. They're not diverging. See, a laser beam diverges. The individual photons are diverging. But polarization, technically, true polarization, such a thing, the beams would be parallel, the polarization would be parallel. So it'd be the same distance no matter how close or far away you are. The polarizing film would work equally well. And I think when it comes to polarization in things like radar, you will find that the filter doesn't work as well up close as it does in the middle or towards the target, that it changes how well the filter filters.
Is oscillating like this. Later we're going to add all directions that we want to. I just picked one now.
So it's not oscillating. It's polarized. The photon is a little bit... The two rails of the train track are further apart. The rails. That's all.
And here are my fine dust particles. And these dust particles have electrons. And the electric field passes by. And these electrons, which are charged, are going to...
Okay, again, so this electric field passes by and moves the electrons, which just doesn't make any sense. I mean, it should not make any sense to people who have any kind of reasonable skills. That photons have to hit electrons. They can't just go by and cause disturbances that the electron reacts to. No way. It's an energy conservation problem. It just can't happen because that's invented energy, and there's no evidence that photons have variable amounts of energy. Those have been established in experiments. We know the whole word quantum comes from this fact that there's an explicit amount of energy in a photon, and you can't get more than one. Like, if what he said is true, you could have a photon affect some electrons over here, and then affects them over here, and affects them over here, and another electron wouldn't affect any. And they'd have very different energy profiles then. There's no evidence of that.
Oscillate in this direction. They're going to experience an acceleration, which is the force that they experience divided by their mass, and therefore that is the charge that they have, times the electric field divided by their mass.
So you could write the same formula if you just say they hit the electron. The same, all this would still be this, the same influences are the true here, except for this F word. Just say that's bang, that's hit. The hit force. And then that's your momentum. And then I'll create a new momentum in the electron. So this is just very... This explanation is, like many, one explanation in one context is different than the explanation in another context, and as long as they keep the two subjects far enough apart, it keeps people not realizing he just contradicted himself. One lecture he says this lecture he says that. You know.
So as this electric field vector, this electric field component oscillating with frequencies omega,
not happening,
is passing by these electrons.
He said it's one photon. That's how he started, right? So let's be consistent. He said he starts with one photon. Now, oscillating might happen with a bunch of photons. At any 1 minute, you have more energy this over here and a little less over here, and the laser beam can be variable in terms of its intensities, and you can have oscillations with groups, but an individual photon isn't doing any oscillating.
They themselves are going to oscillate with frequency omega, and this is the force that they will experience. This is the acceleration that will experience.
Right. So they gain an acceleration, and that happens not because the photon flew by. It happens because the photon directly interacts with the electron. Just a fact. And the electron has to either absorb its energy or reject it. I mean, it absorbs it and immediately rejects it, or it absorbs it and keeps it for a while. But those are the only two choices here. And all this is just made up nothing. This doesn't have any coherent, it doesn't make any coherent sense if you really are rigidly interested in conservation laws.
Notice that the electrons will experience a way higher acceleration than the protons, because the protons have a mass which is more than 1,800 times larger than the electrons. So,
right, but the electrons aren't ever going to interact with the protons because they're locked away in a little tiny nucleus far, far away.
Whatever follows is really the electrons that do the job and not the protons.
So unless he's got that right. Yes. Whatever follows, this photon force is an electron-specific force. It messes with electrons more than it messes with protons. It's clearly the electron force. This is the negative pole of magnetism, essentially, at a frequency.
So we have charges that move up and down, and now comes the question which we have discussed earlier, so this is just simply to refresh your memory. If you're here at point P, in what direction will you now see electromagnetic radiation that is produced by charges that are being accelerated? We discussed that earlier, and we even had a movie about that.
Right, and again, you said this is a single photon, so again, none of this is happening.
And perhaps you will remember that the electric field at point P is now oscillating in this direction. A spherical wave goes out if I accelerate charges here. And the rules...
No, you hit an electron, the electron moves in a direction, and if it rebounds, then it readmits the photon as a reflection.
About this direction of the electric field are very simple. E is always perpendicular to the direction of propagation, which is the position vector. I call this the position vector R. And the second rule is that A, R, and E are in one plane. And that happens to be, in this case, the plane of my blackboard.
It's not a very good perpendicular drawing, in my opinion, since you should have had the vector going the other way to be perpendicular, but whatever.
But of course, that doesn't have to be the plane of the blackboard, because I can choose my point P in space here, and these rules still apply. The incident photon, which in this case I picked only one, is completely destroyed, absorbed by the dust. And the electrons which are going to radiate...
All right, so again, does it make any sense? Their theory is the photon flies by the electron, somehow makes the electron move, and then just falls apart and dies or something. It's just a wrong way to describe the event. A single photon hits a single electron. That's what happens here. There's no field interaction between the two. It's a direct hit.
Re-radiate a photon.
There you go. So it absorbs, the electron absorbs the energy. It moves as long as it has the photon, so to speak. It's like a piece of silly putty, and a little piece of silly putty hits it and becomes part of it. And then if it moves back the other way, that is, if its velocity from the new little piece is stopped, the photon's coming back.
exactly the same frequency. Because if this is oscillating with angular frequency omega, then the acceleration will be with angular frequency omega, and so this E field will have angular frequency omega. So it really is as if the photon comes in and takes off in a different direction. That's why we called it.
Yes, exactly, and that's exactly what does happen, and it's exactly that mechanical, and that happens in the two-slit experiment. It happens in all these experiments. You're just changing the angle at which the photon travels. There is no waving stuff. There's no interference garbage. There's just angles that photons leave at.
Is scattering. So the frequency remains the same, but the direction changes. And the probability that that photon will go in this direction or this direction is 0. Because you remember that no electromagnetic wave is propagated in the direction of.
Well, it obviously can't go in any other direction, quote unquote, than the energy in, energy out equation is going to require. So it just depends on how elastic or inelastic the electron's position is. So the more inelastic it is, so it can, again, as I pointed out, the electron can be pushed in this way, and the other electrons are going to push it back. Forces will be hitting it, and it will adjust its position based on those forces and then rebound. It will U the turn.
The acceleration, there's a high probability that it goes out in this plane, perpendicular to A, and at this angle theta, the probability is a little lower. We discussed that earlier. Now I'm going to convince you why light that scatters over 90 degrees, that comes in like this, and then comes to you, why that is 100% linearly polarized.
Right. So the point is that the Brewster angle is one thing, okay, 100% polarized, but everything after that is apparently also 100% polarized.
Here is a beam of light. And this beam of light is unpolarized. That means if I look down on this beam, you have individual photons, and I describe to those, maybe a little bit artificially, but I will do that. It was successful with Malus law. I describe to them individual directions of polarization. So each photon on its own has a uniquely defined direction of polarization. It is a picture that is not kosher. You really need quantum mechanics to do this right. But on the other hand, the result...
No, you don't. You just need to understand that every single electron and every atom is in a different position, and the movement of the electrons are going to be in different positions. So it's not that complicated.
The result that you find is probably correct. You will find the same result if you did it in a quantum mechanical way. So here you have these dust particles.
No quantum mechanical way.
And so what is going to happen is, this light comes in, and then one may be scattered in this direction.
Let's understand, quantum mechanics requires you to already know what the probabilities are. Okay, it doesn't predict the probability. It already has a statistical experiment or something else to give it the statistics, and then it just formalizes those facts. But that's it. It can't do anything without knowledge ahead of time of what the outcomes are.
Another one in this direction, another one in forward direction, and you can go in all directions as you please.
Well, you can't go backwards, so you can go in all the directions you please. The movement of the electron will likely be in one of the forward directions, certainly by probability a lot more than these higher angle positions.
I'm now going to look in the plane perpendicular to the blackboard. Because in the plane perpendicular to the blackboard, every photon that ends up there is at 90 degrees angled. It comes in like this, that is 90 degrees, this is 90 degrees, this is also 90 degrees. And here is that plane. I just draw a circle, but there's nothing special about the circle. And so the photons come now straight to you, perpendicular to the blackboard. That's the picture that I have now in mind. And let's say you are looking here.
I think the better picture is just to point out if they're going straight up, they go 90 degrees, and it's kind of, got it, right into my eye. Like a laser beam. If you see a laser beam going through dust, the air in my house, you'll see the beam. All those photons are coming at you at sort of 90-degree angles. There's no other way you could see them, really.
So you are sitting there, so you have to lift this up, and you're really sitting there. So this is where you are. And let's take one photon that comes in, which happens to be linearly polarized in this direction. We pick one photon, but it's unpolarized light because we're going to add so many photons that on average there is no preferred direction. But I pick one to start with. And now I ask myself the question, if that photon is scattered in your direction, in this direction, how is the E vector oscillating here? So this is now the position vector R, and this is the direction A in which the electrons are going to shake. Because the photon comes in with an E field shaking like this, so the electrons are going to shake like this. And you will immediately conclude that the electron...
So again, the electron is going to move, you know, depending on the angle. So if the plane of the atom is this way, and the electron's, you know, on a plane, and you hit it from this kind of angle, well, you're going to be hitting it in two directions, towards the proton this way and down, you know, away from the proton and still towards the electrons, though, the other electrons. So it's going to be moved back at some other angle and shot back out, but it's always going to be in the same plane in the sense that the energy this way will be retained. You know, it'll come back this way or you know, some other towards me way. It won't come back this way or that way.
The electric vector here must be oscillating like this. Why? Because it has to be perpendicular to R, which it is, and it has to be in the plane of...
See, they have no clue how photons, what a photon is when it's inside an atom, how it functions, what it does, anything. So they're just making this up as this fieldy, wavy bullshit, and they have nothing as a foundational elemental theory about how any of that happens. There's no way they could draw you a picture of it. Because the electron doesn't do this. It doesn't go this way and then stop, and go this way and stop, and go this way and you know, in some kind of magical way. Electrons only go and stop because some other force acts on them. Newton's rules. All right, it doesn't change its inertia unless something acts on it.
A and R. There's only one solution, and then this is the correct solution. Now there is a next photon coming in. And the next photon, I'll give it color just to distinguish the two, happens to be oscillating in this direction. And I ask myself the question, if that photon is scattered in your direction, in what direction is the E field oscillating? And you'll come to exactly the same conclusion, in this direction. Why? Because it has to be perpendicular to R, which it is, and it has to be in the plane of A and R, and that's the only solution. A little later, there is another photon that comes in. How is that electric field being observed here? Of course, in this direction. And so, no matter how they come in, on polarized light, you will always see that if the photon is scattered over night...
It's such a deceptive way of drawing this, because the point is that photons go this way, that way, go all kinds of angles away from you. And only one group are going to be pointed towards you. So the ones where the polarization lines are in a different configuration are the ones that aren't going to you. The ones that are going to you have to be lined up that way. They have to be. So it's very deceptive.
90 degrees, you will always see it polarized in this direction, and therefore you have created linearly polarized light. So if you watch here, that is at 90 degrees angle, or if you watch here at 90 degrees angles, but of course it's a whole plane, then you end up with 100% linearly polarized light. If you go through the same exercise, say at an angle here of 45 degrees, and you look here, it's only partially polarized. Indeed, if you rotate in front of your eye polarimeter, you will see clearly light intensity change.
So 45 degrees is partially, we already know that. But it would 57 degrees or 56 degrees, the Brewster angle, that would be 100%. And would everything after 100% be 100%? I mean, everything after the Brewster angle, does that get remixed as a mixed polarization, and then we just have this fancy 90-degree thing is convenient? So that's not made very clear. I don't know the answer, but I'm surmising that everything after the Brewster angle is 100% polarized.
But not 100% polarized. You couldn't turn it into darkness. And if you look from above, and you may want to go through that exercise for yourself, you will see that the light remains completely unpolarized. So it is only the 90-degree...
There's no way you can look from above because the original light is going into your eyes. So, duh, yeah, it's 100% unpolarized because you're looking at the original light. Yeah, okay. I mean, obviously didn't hit anything.
The angle that is very special. And that's what I'm going to demonstrate to you. But before I demonstrate this, there is something that I have to tell you, that I cannot hide from you. I wish I could, but I can't. It's not something that is my goal during this lecture. It has nothing to do with polarization. But that's the fact that the probability, when you scatter light of very small particles, much smaller than 1/10 of a micron or so, dust particles, that the probability of scattering is way higher for blue light than it is for red light. The shorter the wavelength, the higher the probability. If you ever take 803, you're going to see a derivation of that, a quantitative derivation. Blue light has a 7 times higher probability to be scattered than red light. And so in that...
So the point being is the red light has a more regular vector, where the blue light has irregular vectors. One way of saying it. Another way of saying it is blue light has more elements in it, so more likely to change direction, more impacts. It's pushing electrons deeper, so to speak, and therefore has a more likelihood of changes between the impacts because there are more of them.
If I'm going to do my scatter experiments on very fine particles, you will see that that light is going to be bluish. You can't miss that. Now, if the particles of which I scatter are larger than 1/10 of a micron, say 1 micron, this effect of color on probability of scattering is highly reduced. And if I scatter of very large...
So big stuff doesn't make a distinction between little, the smaller frequency photons and the bigger frequency photons. So that might have more to do too with the, I'm just trying to think of how the blue light has a tighter polarization. So it's going to be more successful. So he said it one way, right? He said blue light is 7 times more likely to get to be scattered by small particles. What he should be saying is red light is 7 times less. That's the key. The red light is the thing that's changing its behavior, not the blue light. See, this physics is tricky. You gotta analyze each little piece and say, wait a minute, wait. Which one is fucking up here? Which one is messing up?
Large particles, then there is no dependence anymore at all. And in this lies the secret why the sky is blue. I will get back to that later today. The reason why cigarette smoke can be blue if the smoke particles are very small, and it's the reason why clouds are white. Because the sunlight hits the clouds, the light scatters, but the water drops in the clouds are several microns in size and even larger. And so there is no preferred wavelength that scatters, and so the clouds look white.
So there's no excluded. So again, you're not excluding the red from the scatter, where the red gets excluded from scatter at very small particles. So again, it's just the way you say it means something.
And so the first demonstration that I want to do is very much like what you see here. I'm going to send unpolarized light up here, straight up. We have bright spotlights there, and the light goes straight up. In here, I'm going to put very small dust particles. And I've decided to do that smoke, simply cigarette smoke. So I'm going to hold cigarette smoke in these beams, and the light that will come to you, no matter where you sit, must have scattered closely over 90 degrees, right? It comes up like this, but if you see it, almost for everyone in the audience, 90-degree angle scattering. So with your linear polarizers, you will be able to see that that light is polarized. It's going to be polarized in this direction, which is the direction that I have here.
And they always have those directions wrong, so if he says it's this way, then it's really this way.
The first thing I'm going to do for this demonstration. So I need cigarettes and I need smoke, as much as I hate this.
So this is where we just pretend to be too stupid to figure out obvious things. Like, obviously he's a chain smoker. Okay, there's no way some regular person could do this with cigarettes. I mean, no regular person could do it. It'd have to be a smoker. And you have to be a heavy smoker.
Okay. That should do.
Always got to do a little cartooning. But again, no, like I said, nobody who hasn't smoked could do this. It would make them sick. They just forget it. No way. No way.
Okay. So you need a lot of light. And this light comes presumably from here.
It's like a $50 experiment. Nowadays.
Yeah, there it is. Ah, ready for this? Okay, so have your polarizers ready?
Really won't need them.
I want you to see two things. Number one, that the light is bluish, and number two, that it is polarized. Take your time for that. If you don't see it as blue, then the reason for that is that at low light intensities...
It's kind of neat that the cigarette itself has a blue tinge to it. And there's no real sign that smoke is traveling along the cigarette, but it's something like that must be happening for that to happen, right? Why is the... or maybe it's just the reflection off the white paper is more likely to reflect blue. There's something about the cigarette or the paper that's creating a blue streak right across the paper there.
Your eyes are not very sensitive for color anymore.
Could be a reflection off the smoke. You know, a secondary reflection.
Looks quite bluish to me, though. Now I want to do something in addition. I mentioned that if the particles grow in size, that the scattering is no longer preferred in the blue. And I can demonstrate that. I can kill two birds with one stone. What I can do is I can hold...
You can create more scatter in the red. Yeah. By making the particles bigger. And now the red light variance won't be a problem. The fact that the red light is polarized wider than the blue light, more variability, will not eliminate its capacity to do the 90-degree reflection.
Put the smoke in my lungs for a while, and when I do that, the water vapor in my lungs will precipitate on these dust particles, and they will form small water drops. And when I puff that out, you will see a distinct difference in color between what you see now and the smoke that comes out of my lungs when these particles are 10 microns and even larger. You will see then that the light is whitish. So this comes extra, over and above. It comes for free. In order to make you see the difference, shortly before I puff out the smoke in here, I will again show you this smoke as it is now, so you can compare the colors. And you will see that there is a difference. Even though it may not look very bluish to you, for reasons that I mentioned. In darkness, you don't have a very good sensitivity for color. So I'm going to hold this smoke now. As much as I hate it, this is one of the worst demonstrations that I have to do. I hold it in my lungs.
Yeah, such a liar.
For a while.
College students can't handle the truth. So again, somebody who doesn't smoke, no way they could inhale all that smoke. Hold it, no way.
I see a huge difference. I'm very close. The second puff was very white compared to the first one. So we were able to catch two birds with one stone here.
And do some lying. Pretending.
The sky is blue because of this phenomenon. Here, you are standing innocently on the earth. And sunlight is coming in onto the Earth's atmosphere. The sun is there. The sunlight comes in, and the
sort of a You know, probably should have drawn it coming in sideways more, but whatever. It's okay.
Light scatters. And the light that reaches you, that scatters of these extremely fine dust particles, and it also scatters of the air molecules themselves. There are thermal fluctuations that go on all the time, which causes density fluctuations in the air, and they are sufficient to act as scatterers. And so if light from here comes to you, the chances are that it is blue, because it has a higher probability than red. And this is also likely to be blue. And so when you look at the sky looks blue. That's the reason.
There's less stuff above you than there is sideways to you, is the simple way to describe it. So obviously you're on a surface, a round surface. This distance through the atmosphere is much shorter than this distance through the atmosphere. So obviously the light has been scattered by a lot of particles, and some percentage of them are small ones. So the small particles are not doing the red thing. They're not scattering the red light, so the red light gets to you on the small particles. Yeah, and the blue light is the ones that are getting scattered more, and they get all used up going through the thick part of the atmosphere. So all the blue ones get used up going through the distance, but the blue ones aren't used up going up and down through the straight line. This doesn't explain why it's more blue. There's less big particles, and there's a lot of little particles going straight through. The percentage of big ones to small ones is much higher going straight up than going this way. That's it.
Has to do with this strong preference for color to be scattered when it is blue light. If you look in the direction of the sky at an angle of 90 degrees to the direction of the sun, the sky is also linearly polarized for the reason that we now understand, because there is scattering over 90 degrees. And so when the sun is out there, there's always a whole plane, a great circle in the sky, which is 90 degrees away from the sun. So when you come out with your linear polarizers, as soon as the weather clears, look at the sky, at the blue sky, and look 90 degrees away from the sun, and you will see that the sky is very strongly polarized. If you look at angles different from 90 degrees, it's partially polarized, but not as strongly polarized as it is at 90 degrees. So this expression...
So just recognizing that everything you see of the sky is a reflection off a particle, technically. There's no sky without the reflection. So even when you're seeing a blue sky, you're not seeing nothing. You're seeing a particle somewhere between you and the space. That's why it's not black. So light is being reflected off the sky particles. So yes, and it'll be blue more than red, because the red isn't getting scattered towards you, isn't reflecting off as many particles as the blue light does. The blue light hits a lot more stuff than the red light hits. It's more likely to hit stuff, put simply. So you see it as blue because the blue light was more likely to hit a particle. The red light just kept going.
In a very natural way, why...
Or the red light got destroyed and turned into heat, which makes sense when you think about it.
The sun when it rises and why the sun when it sets, why the sun is red. Because if the sun rises or the sun sets, the sun is near the horizon. So now the sunlight comes in like this. Imagine how much atmosphere it has to travel through, how many scattering particles it will encounter on the way. And so right here there is scattering, there is blue light, there is blue light, there is blue light, there is blue light, that has a higher probability, there is blue light. So what do you think is left over for you? There isn't very much left over. What is left over? The blue is gone, the green is gone. So if there's anything left over, it is red. And it is that red light that you see. That's why the sun looks red when it sets, and it looks red when it rises. The same is true for planets and bright stars and the moon. When they're just above the horizon, they look very reddish. And if there happens to be a cloud here in the sky, well, the cloud will also see that red light. So you get a red cloud. And that's exactly what you see at sunset. All these clouds turn red.
Yeah, well, I think the clouds are actually doing some of the scattering, so they're going to look red because they got lots of small particles around them, and so they've absorbed the ultraviolet light, and now all you're seeing is the reflected red.
And so that is, again, the consequence of the fact that the probability for light scattering of blue light is 7 times...
I mean, the water droplets in the clouds are probably big, but the ones around the clouds are probably tiny. The ones that are forming the cloud.
Larger, roughly, than the scattering for red light. So it explains both the blue skies and the reason why the sky, by the sunrise and the sunsets, are red. I can show you two slides whereby you do see this phenomenon, that light that scatters to you becomes bluish. We can see it in astronomy. And the first slide is a picture of the Pleiades, called the Seven Sisters, very hot stars. They are surrounded by very small, fine dust. And the
So again, these are all their story of what we're going to look at. So I'm not saying it's not true. I'm just saying they make these stories up about what they're seeing based on what they've, a ton of assumptions about how far away it is, how bright it is, how much energy it has, how local the energy is, all that stuff. Lots of assumptions made.
Light that reaches you is not only polarized, which you cannot see, of course, on the slide, but it's also bluish. And so let's take a look at that first. So here you see the Pleiades. It's called the Seven Sisters. Some people think there are only 7 stars in there, but there are hundreds. And you see here these very bright stars, and here you see the dust surrounding these stars, and this is distinctly blue.
All right, so this is another piece of evidence about, well, what are you seeing when you see red shift then and blue shift? Because if we make this assumption that there's this heavy density of particles around these, the typical stars, wouldn't that be cause to wonder about this blue shift, red shift thing, and why is, maybe in some cases there's just hydrogen atoms, or there's some other, simpler elements because they're newer stars, and then older stars might be producing heavier elements, and so therefore the scattering is different. So just opens doors to speculation about what they're seeing when they claim something.
That's the effect. The fact that short wavelengths have a higher probability to be scattered than long wavelengths. So the blue has a higher probability than the red. And the next slide.
And again, that might just be because the polarization, because the alignment is likely further off. Blue light probably has a narrower polarization. The distance is narrower than the red. It's probably commensurate to the frequency is the width of the polarization. You could argue that microwaves are like, a half, like a centimeter, their polarization. So their wavelength is 3 centimeters, their polarization is a half centimeter. So you could use that as a post, a statement that the polarization width is 1/2 the frequency distance between. And so if you did that with light, then you could come up with like some, nanometer number that is the actual polarization, and that defines how, whether or not in certain energized particles too, moving ones, whether a photon can hit it at a higher, longer frequency, because it's not going to be in the same place anymore. So a single electron can't receive the energy from the photon in complete form, because it moves before the next bit of energy arrives.
Shows you a man on the moon. And this person is walking on the moon, but as he walks on the moon, he produces dust by just walking. Very fine dust particles that come from the soil that he brings up. And what he's doing, he's creating around himself sort of a blue atmosphere, a blue sky, because the sunlight comes from the right. And so the light that you see that comes in your direction is being scattered, of course, because there's no air on the moon. So it can only be the dust that he has produced. And you see that dust is blue. It will probably also be strongly polarized, because if it changes 90 degrees angle, then of course it would also be strongly polarized. Now I want to do a demonstration, the last one, which catches more than 2 birds with 1 stone. It's going to kill 3. I have here a bucket with thiosulfate. And we have light coming from this side, which we shine through that bucket. And we're going to put a little bit of sulfuric acid in there. And when we do that, sulfur will precipitate, small particles of sulfur. These small particles of sulfur will become the scatterers. And so this light, which is unpolarized white light, will begin to scatter. And you're going to see it. If you're sitting at right angles, then you will see that the light is linearly polarized. You can enjoy that. If you're sitting there, you're not so well off, because then the light is not at 90 degrees. But you will see it partially polarized. If you're sitting there, it's not at 90 degrees either. You will see it partially polarized. But you will also see it blue, because the probability that blue light scattered is higher than red light. So you're going to see slowly in front of your eye, a blue sky is going to develop. It's going to be polarized in the vertical direction. For those people who are sitting at right angles, partially polarized for the rest of the audience.
Right. So the point will just be is obviously the blue light's going to be leaving perpendicularly, and the so we're going to have more red light in your byproduct, your end product.
And then we're going to look at the light that remains after the light had penetrated the atmosphere, after the blue light is slowly exhausted. All right. I will also take a polarizer with me, so I can also show you then the polarization. Let me first put that sulfuric acid in. I will do that now, so that I know that okay. So very slowly am I creating now my own atmosphere, and I'm going to make it completely dark. And so you see white light. Keep an eye on the bucket. The bucket cannot be seen by all of us so well, depending upon where you sit in the audience. But I can already begin to see that it turns slightly bluish. Of course, I'm very close. I admit I'm very close, which is very good. It's slightly bluish. More and more sulfur is going to precipitate as time goes on. We have to be a little patient. Oh boy, it's bluish. I'll show you that it's polarized. I rotate in front of it the polarimeter. You see there's a distinct polarization of this light if it comes out at 90 degrees. More and more sulfur is precipitating, and look at the sun. If you think of this as the sun is getting a little yellowish. It's not so white anymore. And you wonder why? Well, you should be able to answer that now, because the light that is scattered in the atmosphere, I call this the atmosphere, is blue. It has a higher probability than red. And so what is left over?
Right, but proportionally, you could argue that the blue is more likely to do the 90-degree thing. So the red is still doing these other angles.
In the direction that you see on the screen there is the remaining light. And the more blue leaves and the more green leaves, the redder the sun is going to be. And if we're going to be a little bit more patient, and we certainly have the time for that, you're going to see the sun getting pretty bloody red. So keep an eye on it. Also have your linear polarizers and try to see that the light that comes to you from the atmosphere, if you are at 90-degree angles, I will once more do it with my polarizers, that's strongly polarized. Oh boy, look at the sun. We're getting close. We're getting close. Imagine you're now on the beach, very romantic, and there is the sun. You with a friend. You don't have your polarizer. Well, from now on, you should always have your polarizer with you, of course. You can really impress your friend, believe me. For one thing, you can point out that the sky at 90-degree angles from the sun is nearly 100% polarized. You can even tell your friend why the sky is blue. And then as you experience this romantic sunset, you can also explain why the sun is getting red. Because all that blue light and the green light gets out first, and this is then what is left over. And the sun is really beautiful now. I already feel these butterflies in my stomach and ants in my pants. This is sunset.
Ants in his pants. Yeah, I'm not getting that vibe.
All right. This is very, very nice sunset. Oh man, what a beautiful sunset. Yeah, indeed, indeed. We are approaching sunset. Okay, see you Wednesday.
Yeesh. Again, I really just don't have I don't do any of that charming sense of humor stuff. Unless I'm the one being charming and funny. But anyways, okay, so I think we've killed this subject enough. So till the next time, and such, so forth.